let's do our first hybrid proof. Remember, our theorem is that if this PRG with n+1 bit output is secure, meaning that the output of this, the n+1 bits here, is indistinguishable from n+1 random bits computationally, then we are going to prove that this n plus pn bit output PRG that we constructed here is secure. Our proof style, remember, always goes through adversaries. So what we are going to prove, remember, is that if there exists a probabilistic polynomial time adversary A that breaks this new construction we have, Gn plus Pn. Remember, breaking here means distinguishing the output of Gn plus Pn from random output of the same length, n plus Pn bits, with non-negligible advantage. Then we are going to construct, remember, another PPT adversary. Let's call it B. And B is going to break this underlying primitive, our assumption here, Gn plus 1. So if there exists an adversary who can break this, then we will construct an adversary who can break this. If the adversary who breaks it is probabilistic polynomial time, then ours will be probabilistic polynomial time as well. If this adversary has non-negligible advantage, our adversary will have non-negligible advantage as well. In this proof, we are going to employ hybrid technique. Remember, our hybrid definition was as follows. Hybrid I would mean pick n plus I random bits and then continue this construction from level I. Okay? So start with n plus I random bits, continue this construction, and with n plus Pn bits. Let's define our adversaries. As usual, we are going to do it visually. So we will draw these two boxes. Inside, there will be the adversary A. Adversary A is playing the game for PRG n plus Pn. What's this game? Remember, the adversary is given the security parameter together with some value, let's say W, such that this W is output of Gn plus Pn or completely random of the same length, n plus Pn bits. At the end, this adversary is going to tell us whether this W is pseudo-random or random. That will be the adversary's output. This adversary B that we are going to construct is playing the game for Gn plus 1. So it will be given the security parameter for that game, which happens to be the same here, and some value, let's say R, okay, such that this R is either the output of Gn plus 1 using some random n bits input, or it is completely random n plus 1 bits. And our goal as B is to again say whether this R was pseudo-random or random. So B needs to construct these hybrids. For now, assume that we have a fixed value of I. So our goal is to construct either HI, okay, or HI plus 1. Remember, the only difference between hi and hi plus 1 was one more run of this gn plus 1. So our goal is to construct either one of these. Essentially, we will not know which one we constructed. But that's good, because the adversary will help us know which one we constructed. So we want to construct either hi or hi plus 1. Let's do that. What we are going to do, the hybrid says pick random I bits or I plus 1 bits input. So in every proof, remember, the outside adversary B is trying to tie its input to somehow the input of the inside adversary A. That's the main mechanism of every proof, every reduction proof that we are doing. So somehow my hybrid construction should include this R value. So what I am going to do here is I will start from R, okay, at level I, and then I will run this construction from level I starting with R, okay, and then obtain what will be an n plus pn bit output. I will call this W, and I will send this to the adversary. Of course, now we need to think carefully. Remember, this R is only how many bits? N plus 1 bits. So the n plus 1 bits of R is coming here. But level I requires n plus I bits. So I need I minus 1 extra bits here. Okay. And these I minus 1 extra bits, let me call it S, and I am going to pick those randomly. Okay. So I am going to pick I minus 1 extra random bits, concatenate with R. Now start with R together with S at level I. Do this construction continuing from level I. Obtain an n plus pm bit output. Send this as W. What did we do here? So here, let's consider two cases. There are two cases. Either R is computed as follows. Some, let's say, X value was chosen randomly such that it is n bits. And then R was computed as running G n plus 1 over this X value. So this is the pseudo-random case of R. Now, what about the random case of R? In the random case, R was actually chosen completely randomly from n plus 1 bits. Now let's think about what we did here. Consider the case that R itself is completely random. So essentially what we did here is the following. We have n plus 1 random bits. We have I minus 1 random bits here. So in total we will have n plus 1 plus I minus 1, n plus I random bits. So we started with n plus I random bits, reached to a W. This would correspond to essentially hybrid I. This is exactly the definition of hybrid I. What if R was pseudo-random? If R was pseudo-random, here is what would have happened. We would have started with some random values here, and then R would have been computed. Okay, so R would have been here. anything extra here would have been transferred here. So why would this correspond to hi minus 1? Think about it this way. If r was computed as an output of gn plus 1 over some random x that is n bits. So x was here, that is n bits. And then there were I minus 1 random bits here. R is computed, okay, R is n plus 1 bits. We copy these I minus 1 random bits here. So overall, we would obtain n minus I bits, sorry, n plus I bits. Now, what would this mean? This would mean that we essentially started with n plus I minus 1 random bits. We ran through one level of this, obtained R pseudo-randomly, and then I minus 1 bits again, and continued, of course, until we obtain some W. So we started at level I minus 1 randomly, and then essentially continued running the construction from there. This is why this corresponds to hybrid I minus 1. So if R was random, this would have corresponded to hybrid I. If R was generated pseudo-randomly, this would have corresponded to hybrid I minus 1. So we sent this W to the adversary. The adversary tells us random or pseudo-random. Think about it this way. Which hybrid is more random? Essentially hybrid I, because hybrid I minus 1 involves one more run of this pseudo-random generator. Therefore, if we generated hybrid I, we expect the adversary to say random. And when does it happen? It happens if R itself was random. So if the adversary says random, we should say random. If instead R was pseudo-random, this means we have generated hybrid I minus 1, and we expect that the adversary should say pseudo-random in that case. So we should also say pseudo-random. Essentially, the last part is extremely easy. We just say whatever the adversary A says. Are we done? Almost. The only issue here is our adversary B needs I. It doesn't know I. We don't know I, so what we are going to do is we will pick I randomly. And I will be anything between 1 up to Pn. Okay? So I is some value between 1 and Pn. If we picked I as 1, and if the R value we are given was pseudo-random, then we would have obtained hybrid 0. If R value was random while we picked R as I as 1, then we would have computed hybrid 1. Now, there are some more things we need to argue. So what's the underlying idea of the proof here? Remember, we have hybrid 0 and hybrid Pn that needs to be indistinguishable. So in between there are these other hybrids. Hybrid 1 here, hybrid 2 here, hybrid 3 here, some hybrid, let's say I here, hybrid I plus 1 here, etc. Consider this case. If the adversary has only negligible advantage in distinguishing these neighboring hybrids, so between each neighboring hybrid, the adversary has negligible advantage, let's say. Remember, we have Pn such neighbors. So the total distinguishing advantage between hybrid 0 and hybrid Pn would be Pn times this negligible value. Now remember, Pn is polynomial. If each one of them are negligible, this whole thing would be a negligible value. On the other hand, distinguishing between hybrid 0 and hybrid Pn means this whole distinguishing advantage is essentially some non-negligible value. If this is non-negligible, what we need is the following. This sum is non-negligible. If all of these were negligible, the sum had to be negligible. Therefore, at least one of these neighbors here must be distinguished with non-negligible advantage. So if H0 and HPN can be distinguished with non-negligible advantage, at least one of the neighboring hybrids must be distinguished with non-negligible advantage. At least one. Maybe all of them can be distinguished by non-negligible advantage, but at least one of them need to be. Therefore, consider that the distinguishing advantage of the adversary A is, let's say, some epsilon of n. By this logic, the distinguishing advantage of adversary B would be greater than or equal to epsilon n over Pn. Why? Remember, if epsilon n is non-negligible, at least one of these neighbors can be distinguished with non-negligible advantage. But we are picking a neighbor randomly here. There are Pn such neighbors. We are picking one randomly. So, if we picked the right one, where the adversary has non-negligible advantage, then we will also win. If we picked a wrong one, we wouldn't win. What's the probability that we picked the right one? There is at least one of them that is right, meaning that has non-negligible advantage in distinguishing. If there's at least one, and there are Pn many of them, with at least 1 over Pn probability, we picked the right one. So we multiply this with 1 over Pn, but this is a lower bound for us. Now let's conclude our proof. If epsilon n is non-negligible, non-negligible over polynomial would be non-negligible. And final reasoning the other way around. If epsilon n over Pn must be negligible, then epsilon n must be negligible. Therefore, we have these two things. If this Gn plus 1 is a secure PRG, then this Gn plus Pn is a secure PRG. So if this has to be negligible, this has to be negligible. And this concludes our proof.